the next talk is again presented by me, sorry. And I will tell you about our results in a fiber-based seed laser. So you heard already about semiconductor, but as I mentioned, the first presentation, we're also working hard. We were working hard on fiber-based seed lasers, and we have made quite a few actual design because of some observations. So let me go step by step. First of all, the aim requirements, we came to this problem and try to find a solution. It's not so many laser system on the market, special industrial laser system with sub 200 femtoseconds. And there is a reason, because it's not easy to make reliable and at the same time very short pulse separation. But we faced the challenge and was happy to address it. And we also take into account that it requires some environmental stability and also reliable operation. So our system was also tested over 2,000 hours for drop-free regime, similar as a semiconductor laser already presented earlier. So the first design laser, what we made, was based on the so-called NALM architecture. It's nonlinear amplifier loop mirror, or in a society, it's also called 8-shape design of the system. We have a main loop, and we have a main loop and also amplified loop. And this part works as an artificial satural absorber, but serves the main loop, and the laser operate in so-called all normal dispersion regime. The specific of this regime that it allowed to get very high chirp pulses, but at the same time with as close as possible to linear chirp operation. So this led to get not only broad pulse, but also highly compressible pulse down to sub 200 femtoseconds. The laser was made of PM fiber, polarization maintaining fiber, and that gave robustness. We spent quite a lot of time on the design and optimization of the system. This is quite complex, and that's worked, and we achieved quite good results. So here you can see it was packaged in a standard Erlabs package for 2,000 test and operation. This is just to save the system from the students in the lab, or students from the system. This is the output duration of the laser. We first achieved 170 femtosecond pulse duration for 13 nanometer spectrum. Here you can see the spectrum and linear domain. This is linear scaling. This is a very typical spectrum for such kind of laser operating in normal dispersion regime. If you calculate the transform limited pulses for 13 nanometers, is actually 90 femtoseconds. So we start to think maybe something not optimum in our compressor design, and maybe too long pigtails that stretch pulse even more. But before I go to optimization, we have achieved 16 milliwatt output power. This is quite remarkable and very good, as you can you know already, for tapered fiber amplifiers. This is a very good level for input signal, and the repetition rate is 1300 megahertz. They haven't been limited in repetition rate, so this is original design, but it's come out from the optimization. Of course, it can be done smaller, it can be longer if there is a requirement from the particular system. But because 170 is almost almost doubled than the transform limited, we spent a bit more time on optimization of the laser design, also compressor, and find out that we can get better results, 150 picosecond, and you can see that it's very good spectral temporal profile of the pulse without any side lobes. So we think it's very promising, and we can go even further and try to compress it stronger to get better result, and what we've seen it's achieved is 140 femtosecond. It looks like just at a 10-20 femtosecond step might be small, but actually every 10 femtosecond in the sub 200 femtosecond pulses is very challenging task. There is a reason why there is not so many lasers delivering so short pulses on the market. It's not just because laser community is lazy. But we stop at this point. Maybe there is a room for further improvement, but we stop doing anything because, as you can see, we start to see some side lobes at the pulse. It means that if we start to compress it further, we might compress on this middle part, but not. We still will have a residual side bands that also carry energy, and it's not very good for amplification. And there is an indication of nonlinear chirp in the pulse, and this is not very good for amplification. We found solution by using different approach how to overcome this one, but I will come to the second part, to this point, to the second part of the presentation. So let's look at the investigation of the stability of the laser. We have a small video. Let me try to run it if I can. Oops, no, it's, yes, now it's going. Standard labs package, you can see the spectrum here, and we're trying to a little bit shake up the laser gently because it's still needed for amplification afterwards. And as you can see, there is absolute no reaction of the laser system on the knocking by heavy pieces on the package. So that we conclude that it's quite good environmental stability, and also we performed some initial tests on the variation of the temperature. You can see it on the right part of the spectrum. There is some reaction on the temperature variation. This is standard temperature variation in our laboratory. You can come in the morning, it will be a little bit colder because we keep system cooling, and at the evening it's already much higher heat because of all devices working in the laboratory. But laser reacts on this, but reaction is not very high, so the deviation is just 2.2% from the mean value, the maximum power. This is very good result, and we have tested the system for 2000 hours of drop-free operation. And here you can see the spectrum, what we measured during all those hours with the some periodicity. The pink value, because you don't see it because it overlaps, the system performed it extremely well. There was no any deviation in the spectrum, no changes, nothing. The pulse compression and pulse duration of the 2000 operation was absolutely the same. And we started November 2019, and there is somewhere the pink line of the original spectrum, and we end up at the middle of February of the 2020, and this is blue line that's also somewhere hidden here, but if you look carefully, you can find it. So no changes of the spectrum during 2000 operation. That's very good stability presentation. And of course, because we notice the changes in our lab and the temperature, and that's already known result, we have followed the change of the power during all this time, and we measure this overall deviation is as 1% from the mean value. And as we already discussed, it might look as a very big changes, 1 milliwatt power level for high power amplifier, but this changes happening to the tens or hundreds hours of the operation, and no one process continuously during this time. So no problem with the output power escalation of the problem later. So as I mentioned, during the compression of figure 8 laser design, both we find out that further compression down beyond 140 femtosecond gives already the side lobes of the pulse, and we were thinking is there a possibility to improve. We didn't find it within the same design, but we developed a new system what delivered similar tone pulses. The difference compared to traditional pulses, dissipative solid pulses from the laser operating in all normal dispersion regime, this pulses has a parabolic chirp and a parabolic shape and linear chirp inside the pulse. So its compressibility is much better than the compressibility of traditional dissipative solid laser. However, if you start to look at the literature, such pulses working in a they demonstrated it's very beautiful pulses for amplification, but the stability of such regime is very, very poor. So it requires almost constant adjustment of some saturable absorber. If it's based on artificial saturable absorber, non-linear polarization evolution, it constantly requires adjustment of this. And startup process is very complicated. So we're thinking, how is it possible to improve the current state of this kind of design? And we made the special designed laser based on a frequency shifted feedback mechanism. So we have acoustic optic in the cavity. This is a ring cavity. All other components are very traditional for the laser, but the specific is an acoustic optical tunable filter. First of all, it's a filter that is essential to be bandpass filter, essential to be in a dissipative solid on laser, but it's also shift frequency. So it shifts the central frequency of the signal a little bit from the optimum position. What does it mean for the cavity? It means that there is a small amplification for the central part than for the wings. And self-phase modulation and linear effect works in a way that it's shifting the system back. But if it happens only if there is enough peak power in the signal. So there is actually possibility for self-phase modulation to work. If we assume that besides the signal, there is also some instability, what feeling usually is similar to an operation every time in the cavity, it's low power. It's not as high power as a signal always. It's very small, but it's enough already in traditional approach to kill the system. But in this system design, because it's low power, self-phase modulation doesn't work so efficiently as for signal, and it's filtering every round trip time by acoustic optic by frequency shifter outside of the optimum gain position and eventually filter it out completely of the cavity. It doesn't happen within the one round trip or two. There is a certain time when the system reacts, but it happens very efficiently. So as a result, there is only signal what survive in the cavity, and all other noise perturbations, spikes, random spikes due to some environmental instability induced by environmental instability eventually filter out from the cavity. And that gave us much better stability, reliability of the system. But also at the same time, we achieve very short pulses. So here you can see the spectrum. It's in this case 7 broader, it's 2.5 nanometers, 20 nanometers, and we also got 140 femtosecond pulses. But here you can see that we almost free over side lobes. So we compress the pulse to very good temporal profile. We couldn't compress it longer, and that's the reason for that was already the photo dispersion that the pulse gained in the cavity, and unfortunately it was so small that's not so easy to address both second order dispersion and third order dispersion in optimum position. But technique works really well. As you can see from radio frequency measurement signal, this is a signal that's extremely good extinction ratio, but the key point of that is actually here in the baseline. So the wing actually at the baseline of the device. So this is absolute minimum what this device can measure in terms of noise. So we are really at very low noise level in that this is just because approach works very well. This result has been published in a paper in Optics Express. If you're interested in details, more details, and sure you can read. And also we have submitted patent application in USA based on this approach, and it already has been expired by companies, so we sold it up. And this is all from my side regarding the fiber-based seed lasers. I'm happy to answer any questions. Okay,
I have
yes.
just one small one. I mean, the temperature test, that you have done to check the stability, you have been just scanning within ±1 or 2 degrees.
No, it's just a variation was within ±2 degrees.
Because there was a slide, I thought you were just varying when you were having this. This was just the variation that you measure, you mean, of your system. Okay. It's not rising the surrounding temperature and so on. Okay.
Yes, so we have tested is any environment changes, or do we need to introduce, and we find out that it's naturally happened in our laboratory, so we just follow. Okay. And we notice also the following that the laser reactor causing the temperature.
Do you expect problems if you have a gradient of temperature ranging from ±10 degrees, I mean, for your system?
So far, we haven't noticed anything. So during amplification, it works well. So we don't see. Let's see when it will be with the material processing. But according to the initial experiments, this variation as our application doesn't react at all. So few tens of milliwatts, hundreds milliwatts amplified, that will be a noise level for application what we use. Mm-hmm. They need much higher power.
It's just that we are hearing sometimes if there is a leakage in femtosecond, if there is a leakage of 1 or 2 watts, it's too much for the application guys in microprocessing. That's why I was asking, I mean, if this can be an issue,
Yeah, but you can see that at least what we have seen is the changes of environment within 20 hours. So we don't worry about change of the power. But of course, if there is fast changing of the temperatures and something going wrong with the environment, that need to be tackled from this point of view rather from the adjuster laser to this fast variation of the temperature.
Okay.
Yeah. Thank you.
Thank you.
Okay, if we don't have any other questions, let's move in the program. And the next speaker is Vasilii Ustimchik from Ampliconyx company, and he will show the new design of all glass delivered fiber.
Okay, yeah. So I think you should hear me, and also you should see my presentation.
Correct.
So, yeah, good.
Please.
Thank you. Thank you very much for this opportunity to present our results about the basically design and development of the solid core all glass LMA delivery cable. So basically the purpose of this work was to deliver the proper fiber and also manufacture the cable to deliver the coherent beam after the combination. And basically, since we are going to deliver quite high power, and also the radiation will be pulsed, so the peak power was also quite high, we need to mitigate the suppress the non-linear effect, and that's why we started to look into the large material design of the fiber. Mainly, the main, let's say, problem here is when you start to increase the mode area of the fiber itself, the fiber becomes multi-mode, and unfortunately it became, let's say the output radiation become very, let's say, will have higher divergence, and also the beam pattern at the near field and will be quite bad. And material processing, especially engraving, usually require very sensitive to the beam pattern. So first of all, of course, we design the fiber from the scratch. So we choose the solid core all glass fiber type, and here you can see the end face picture and structure. So basically, to increase the core diameter and mod field diameter, we will need to solve how to basically lower down the Na of the fiber. And for that purpose, we designed the multi-layer fiber with the several quartz layers. And basically, one of the main tasks was like to design the fiber which will be bend insensitive, since basically the delivery system is supposed to be flexible, and some bending radius can bring losses in the system. And as already mentioned several times, the material processing can be very sensitive to the change in the power. So our investigation ended up at the particular design, one trench multi-layer fiber with a core diameter of 40 microns, and outer quartz diameter was 840 microns. So this determined by the let's say requirements from the cable manufacturer. So here you can see on the slide the results of characterizing the output fiber radiation. As you can see, the near field pattern was perfect basically, and the far field pattern has some kind of speckle signatures, but it's kind of basically the measurements effects. So the measured mod field diameter was observed to be around 28 to 30 microns. So, and it just coincides with our expectations. So, and yeah, worth to mention that these parameters have been achieved for the pretty low power at the input, and basically because we started to work with the bare fiber first. So after that, we started to yeah, okay. So basically we measured first of all the attenuation using the cutback method, and for the the most interesting region around 1050 nanometers, the optical losses were found to be an acceptable range below 15 decibel per kilometer. So it's quite high losses for standard telecom fibers, but basically our fiber is a bit different, and basically it works using so-called leaky modes. Not exactly leaky modes, but it's kind of very close to the leaky modes, because fiber basically by design has a ultra low Na numerical aperture. So that's why this optical losses is in acceptable range, considering that basically the distance that we need to let's say route the light is pretty small, about 5 to 10 meters, and that's why let's say the losses in the fiber itself would be very low. So after that, we started to test our fiber under the high average power and also high peak power test. So unfortunately, during this test, we realized that ultra low NA fiber, in particular exactly this fiber, is pretty sensitive to the mod coupling if we would like to achieve basically the single mode radiation at the output. But during the test, we observed that all the commercial lens that we have we tested has pretty strong thermal focal point shift, and that's why it was I mean the high average power test stopped just by the 300 watts of average power. But anyway, we tested the fiber itself with the laser parameters at the basically laser operating in continuous wave regime with the average power around 300 watts. So the input beam quality parameter was around 1.3 watts, and the output radiation was achieved at 300 watts to be 2.55 m squared beam quality parameter. So with a transmission efficiency around 85 to 90% over the roll across the whole average power that we tested. So yeah, as I mentioned, we're struggling with thermal focal point shift. And basically, after all this test, it was recommended, it was understood basically that for the power increase, we definitely will need automatic beam coupling system. But at the same point, during the, let's say, implementing the perfect alignment, we was able to achieve the m squared around 1.45. Basically, this is quite strictly single mode regime of the output radiation, and we achieved it up to 150 watt of average power. So meanwhile, the very good outcome of this experiment is that our fiber is quite tolerant to the light coupling imperfection. So basically, the fiber itself is designed to be like that. Because of the single mode fiber coupling usually suffering on all overall ambient condition like a temperature and etc. So that's why even if the coupling will be changed for some reason, we will not achieve. I mean, we will not face to the risk to burn out the system, but the beam profile at the output of the fiber will change somehow, and we will able to, let's say, detect it at the same time and basically compensate for this. Yeah. So the next step was to test the high peak power test, so-called high peak power test. Basically, the goal of this test was to reach the peak power level that the target of the overall pulse system, laser system, and we did this. At the same point, the peak power and the coupling efficiency. I'm sorry. So basically, at the same point, we integrate in our coupling system the basically the mechanism to motorized tilting and tipping the mirrors, and that's why we achieved a high precision of the beam coupling, and basically it allowed us to reach very good beam quality around up to 1.1 m² parameter across the entire available power range. And basically it proved that our fiber itself and the single mode fiber coupling in general required the automatic coupling system if we're going to increase the average power, just for mitigation of the thermal effects that can appear in the lenses and the mirrors itself. So yeah, that's all. Thank you for your attention. Sorry for my young scientist, and I'm ready to answer. I will be happy to answer your question.
Okay. Yes, Marvin, please.
Yeah, thank you very much for this very interesting summary. I am interested by fibers. That's why I want to ask a few questions, if you allow me. The first one is the bending sensitivity, because you show that your fiber is bent. I mean, on the table. Did you analyze this? Because you measured the confinement loss, but you never mention anything about the bending loss.
You're right. It's kind of the further steps of our investigation, but basically it was observed during the measurements that this kind of loss level didn't change significantly during the bending, of course, acceptable bending radius. So this is kind of 20 or 30 centimeters.
Okay. And
so
yeah, go ahead. Sorry.
I mean, for sure, if you will bend it tightly, the loss will increase. But to the best of my knowledge, basically 30 centimeters is quite good parameter for material processing and for the, let's say, older machinery stuff.
And regarding the NA 0.03 you mentioned, what is the accuracy in controlling this NA actually of the fiber? Because typically it's given plus minus 0.1, 0.01, sorry, for the numerical aperture of the fiber.
Right. You're correct. Basically, this is a kind of also for the further investigation steps. 0.03 NA is a measured value. So this is value that we experimentally measured using this for sigma or 1/e² method. So
this is the NA of the mode or of the fiber?
Basically, this is NA of the fundamental mode. So
the NA of the fiber might be a bit larger than.
Yes, it may be a bit larger since basically this is NA for the fundamental mode. Okay. But our fiber, basically, it's not like a strictly single mode fiber in the general understanding of the single mode fiber. There may be some other fibers, transverse modes, yes. That's why here you can see that basically losses in the fiber it's still quite good, around 10%, but the m² is around 2.55. So this is a kind of trade-off. And the maximum m² that we achieved is kind of not the thing that I would like to, let's say, point it out, but it's kind of 3 or 4. But this is in the worst coupling condition. So by adjusting the input light, you can easily reach, not easily, but with a proper precision, you can reach m² around 1.5. So
and very last question, because you brought me to this point now, is the point number 6 in your slide here. You say that you are tolerating the light in coupling or coupling imperfection. I did not get this point actually when you were explaining it.
So basically, this is the same thing. Mainly, the point here is that our coupling system that we are currently developing for this fiber and for these cables basically is targeting to maintain the first thing is a good transmission efficiency, power transmission efficiency, and the second, it's a excellent beam pattern at the output in the near field. So once we detect the degradation of the beam quality at the output, we will still have the same coupling efficiency in terms of power, but I mean there will be no losses in the fiber, and in that sense there will be no risk. So usually commercial cables specified to handle, let's say, 100 watts for 1 hour of losses, 500 watts for 5 minutes, and after that they burned out.
Okay.
But our fiber still can operate without any losses, but it will be detected that something wrong in the coupling.
So you are telling me that the light is still trapped but propagated to higher order modes. That's why you burn it. But the higher order mode have higher losses, so they will couple out.
Let's say you're correct, but this kind of losses have been measured without like a perfect coupling. So this is kind of we basically couple light into all the modes that support it to propagate into the fiber. So it means that this is higher limit of the loss, basically.
Okay, thank you very much. Sorry, I'm very interesting topic. That's why
this is very interesting question, and I guess we can continue to talk about this fiber.
Yes,
and basically, I think that it would be commercially available pretty soon.
Okay, thank you. Bye-bye.
Thank you very much.
And our next speaker is Maria Farsari, and she will show impressive results in terms of very complex shape optical elements for high-power laser system.
Okay, let me manage. I hope I managed to share my screen. Can you see my screen now?
It's promising. Yes, it's
okay. Somehow I cannot see you anymore, but I hope you can see my screen and you can see me.
Yes.
So, hi everybody, nice to see you all here. I'm going to talk to you about optical elements for high power laser systems. So my name is Maria Farsari. I'm a research director at 4th ISL, and I'm one of the 3 Greek partners of PALS. 4th is a research institute in Crete, the bottom of Greece, if you can see in the map. We are the biggest research institute outside Athens with 10 institutes. We're the biggest research foundation outside Athens with 10 institutes, and we just turned middle-aged. We just turned 40, which has its advantages, but it has lots of disadvantages as well. So moving now to my talk, my institute's, my group's work role in PALS was the development of materials and the 3D printing of macro-optical elements for high-power lasers. And this is what I'm going to be talking to you today. Firstly, I'm going to talk to you how we do this using multiphoton lithography. Then I will talk to you about materials, and this was a very big part of our role in PALS. And finally, I will talk to you about some of the applications we've been looking into, micro-optics, but also optical sensors and photonic and electromagnetic metamaterials. And then I will give you one slide basically about how we moving this from research to production. Sorry, there's a bit of a hiccup. So what is multiphoton lithography? Basically, it's a direct laser writing 3D printing technique based on multiphoton absorption. The idea is that we have materials which are gels, but when they are exposed to UV light, they become solids. But we don't use UV, we use infrared, and this has two main advantages. First is that we can go inside the volume of the material because there is no absorption, no linear absorption. And the second is that we can go well below the diffraction limit. And this is a conversation we can have separately in another day. Basically, by moving our beam inside the material, we can directly write 3D structures, as you can see in the screen, and we can write some very complex 3D structures like this microsphere that you can see, which is, there is no other technique to print something like that in one step. What materials we use? We use mostly organically modified ceramics and ceramics. Organically modified ceramics is a very big part of our work. We have been doing it for over 15 years, and we have been developing materials which are hybrid. What does hybrid mean? It's a kind of a way of saying that we would like to work with glasses. However, we cannot process glasses directly using 2PP, which is not fully true, but this is again a conversation for another day. Anyway, a compromise is to take glass groups, ceramic groups, and functionalize them with organic materials. This will give us a lot of the properties, of the good properties of glasses. In addition, it will give us the flexibility we want to structure them with lasers. And this resulting materials, the hybrid materials, have the benefit of both worlds. They have all the transparency and the high chemical resistivity and chemical stability and mechanical stability that glasses have, but they also can be processed. And the beauty of this technology, it's called sol gel, by the way, is that we can mix more than one glasses, so that we can have composite glasses just in a bottle, and we can functionalize them inside their volume, but also on the surface once we process them. Our bread and butter material is a material we developed about 15 years ago, and it's called the Z2080. This is an organic-inorganic hybrid, which has a large percent of silicon groups in it, but also it has zirconium. The biggest benefit of this material is that it can be structured very accurately. There is no shrinkage during the processing. So whatever we design on CAD, we can directly transfer it onto in the 3D structure without any compensation for shrinkage or distortion. So what you can see in the screen now, on the left, you can see a complex photonic crystal for the infrared. That was the original structure we made using this material. And on your right, you can see a complex micro-optical element, which consists of a diffractive optical element and a cylindrical lens. Now, specifically for pulse, we had to develop materials with high laser-induced damage threshold. We worked again with hybrids on the concept that we would like to have a much more inorganic material than organic in the resulting material, in the result. As we know that inorganics have a much higher damage and thermal threshold than organic materials. So what we did, we worked on what we did exactly, you can see it in the paper that's mentioned here, but we used two functional materials. One of them zirconium and the other one was titanium. Both of them we know that have very high damage threshold. but to process them, we had to include silicon in it, silicates. So to test the damage threshold of these materials, we outreached to a company called Lidaris in Lithuania, whose job is exactly this, to characterize, according to this ISO here, the materials that are the laser-induced damage threshold of materials. And we did this test in both for nanosecond pulses and for femtosecond pulses. And you can see on this screen all the parameters that laser used for the laser that was used has the pulse duration and the beam profile and also the pulse length and all the tests. Now there are two kinds of tests in this ISO. There's two kinds of tests. This is a single pulse, and it's the 100 pulse length. So it's called 1-to-1 and 1-to-10. And what does this mean? It means that they use one single pulse to see the damage, and then they increase it. Or they use 100 pulses, which is much more suitable for an application like what we wanted to. The test they do, you can see the damage probability here. Basically, they use a visual test, and they hit it with one pulse or 100 pulses, depending on the test they do, and then they can see if the damage is done. And where they can see visible damage, then this is what the damage threshold is defined. So these are results. As I said, we did both for nanosecond and femtosecond lasers. These were the lasers that were available at Lidaris. And you can see that, and then we went into this publication from 2014, which they had characterized a series of materials used for printing micro-optics. You can see here that one of the materials we developed, which contains zirconium, did quite a bit better at both tests, at the 1-to-1 and the 1,000-to-1, for damage threshold compared to the standard materials which are used, which are the two here at the bottom, Ormocomp, and SU8, the 2015 was the batch of the material. So you can see that the zirconium material we developed had a 33.5 almost damage threshold for the 1-to-1 test, while Ormocomp was 25 and SU8 was 20. Going to 1,000-to-1 test, which is much more practical for the applications we wanted, we had a 12 plus threshold in the material we developed, while Ormocomp was 1. It was and SU8 was 0.5, basically an order of magnitude lower than what we developed. Going to the femtosecond damage threshold evaluation now, you can see that even though the results are a lot closer with the standard materials, still one of the materials we developed had much higher, the SZ3070, and this is describing the content of silicate and zirconia in the material, but and the material that did better at femtosecond at the nanosecond test did also better at the femtosecond test. Now this, as I said, these results are closer, but still the materials we developed give you a higher damage threshold than the materials that are commercially available and routinely used for micro-optics fabrication. Of course, we didn't stop in this damage threshold, and one of the things we wanted to do was to eliminate fluorescence, which is something that's residual to zirconia containing resists, regardless of the what material we use as photoinitiator, which is part of the process that we printed. In addition to that, there's some inherent fluorescence due to zirconia nanoparticles that develop inside the material during the processing. And this fluorescence, we can suppress it using a specific photoinitiator and a specific post-processing technique. And you can see some of the materials here. You can see we can, in this, some of the results here, you can see that we have a visible spectrum with, the materials are extremely transparent, but also they are very low fluorescence. And what you see here is at the top, you see, we used we used it for biology applications, because this is where lack of fluorescence is really critical. But you can see how the structures look into the under fluorescent microscope at the top, and how they look when you put the fluorescent cells on it. And basically, we manage to really suppress fluorescence and see all the visible, the fluorescent biomolecules and cells very clearly, and not see this 3D structure. Moving into applications now, our role in Pulse was mostly micro-optics and optical sensors, but we are doing a lot of work also on photonics and metamaterials, and this was a very important to work on this. So this is some of the micro-optical elements that were developed by one of the young researchers in the group, Dr. Elmina Kaburaki, but also other members. And you can see that by using a multiphoton lithography, we can make some very complex elements that are not available, easy to do otherwise. And this is the specific structure you see in the middle here is a combination of an oxycode and a beam splitter, a prism, which was requested by one of the Pulse reviewers. So this is what it looks here. And this is what all these things look once you put them on fibers, which is another part of the work that we are doing. In addition, we can build a lot of very complex things in fibers, like these gas sensors. You can see here, this is a micro ring resonator. And we also have a Fabry-Perot resonator, which can be used to sense gases. And because all the materials we do are basically inactive, they are not toxic, we can use them for more exotic applications, like this micro-optics we printed, and we checked them. These micro-optics are developed for in vivo imaging. So basically what we do in this, we describe this in this paper, we have implanted animals with micro-optical elements, which can be used to extend the objective working distance in microscopy. And we can also do very complex things like this super resolution imaging with photonic nanojets. This paper should be out. We've already corrected the proofs. It should be out any day now. And it shows how we can include it shows how we can increase the resolution of a microscope by using 3D printed microspheres. Of course, what my community is mostly involved in is photonics and metamaterials. Now, photonic crystals, what you see here, this wood pile structure, was developed, was designed by Kostas Soukoulis about 30, 40 years ago, I would say. And in our community is considered the C elegans of 3D printing. It's what we use to test the resolution of and the possibilities of our materials and our structures. So it's really what we call a reference structure. This is and what we have been working on is to not only to make dielectric structures out of it, but also make structures which can be selectively metallized. And this gives us a lot of possibilities for micro-optics and metamaterials at frequencies which are not optical. And we have been doing a lot of work on terahertz. Terahertz is a fascinating region of the spectrum for us because the classic micro-optics have too much absorption. They don't work. There is a lot of demand for it, for sensing and for general imaging possibilities, applications. However, the optics design is really behind because of the materials, the classic materials that are used for optics, like silicon, silicates, and other 3D polymers, which are used for 3D printing. They have too much absorption and they cannot be used here. So we have been working on designing and developing structures that have exciting properties in these springs. And this is the last slide of research which I will show to you, and it is part of another European project we're involved in. And this is upscaling. How can we make 3D structures? How can we make 3D structures really fast? And one of the ways to do that is use multiple beams. Instead of using one laser beam to write, we use special light modulators, and we split our beam into thousands of beams. And instead of having doing one structure, we can do hundreds or thousands of structures at the same time, depending on what's the SLM size and what we're trying to do, basically. And we can do that independently, so we don't have to be writing the same thing. We can do it by splitting the beam and having full control of every beamlet. So I hope I have persuaded you that multiphoton lithography is an additive manufacturing technique which can employ a lot of materials for a variety of micro and nanoscale applications. And I would like to finish by thanking my group. These are the people that are working with me just now. And there's a lot of other people who have worked in the past with us, and they have been acknowledged in the different publications. And these are the people that are giving us money. So thank you very much.
Thank you, Maria. Do we have any questions from the auditorium? Yes, Marvin, please.
I have one question about the composite material. I mean, what refractive index is expected for this?
Okay, so this is a very good question. So basically, we try to go for as high refractive index as possible. This is what we want both for photonics and metamaterials. The materials I have shown you here have a refractive index of 1.5 to 1.6. However, there are two ways we have managed to increase that. The first way was we have been working recently with a material which is based on titanium nanoparticles. This material, we can structure it quite accurately, and it gives us a refractive index of 1.9. However, its main problem is scattering.
Yes.
So we cannot do classic micro optics with that, because we are limited to an area, to a thickness of about 2 microns. So we have been using it for flat micro optics, Fresnel lenses and Fresnel optics. Another way we have been working on increasing the refractive index is calcination. So we have a material which is a titanium hybrid. It doesn't have the silicate that I described before. It is pure titanium. We structure it and then we put it in an oven at 1,000 degrees temperature and burn in a controllable manner all the organic parts on it. Once we do this, then we get a refractive index of 2.3. However, it's a difficult process. We lose about 60% of the volume of the material when we do that, and we have to pre-compensate for this volume loss. Otherwise, we lose the structures. Basically, the structures are completely deformed. And finally, this process, the calcination process, is not compatible with everything. So we cannot do that on fibers. We cannot do that on chips. So this is what we have to. This is the cost of going for high refractive index.
So therefore, I was just asking this question because of the LIDT that you are giving, because this is typically related to the band gap. General, which is the refractive index of the material. I mean, when you reach something in the 2 joule per square centimeter in femtosecond, this is close to what is silica. You know, silica is
yes. Yes.
And but the silica has 1.45 as refractive index, or 1.448.
Yeah, we're very close to that.
Okay. Thank you. Very interesting.
Thank you.
No, okay. Thank you very much, Maria. We will move forward, and next speaker is Marcel Wolf from Laser Institute Mittweida, and he will tell us about their fantastic technology of polygon scanner and application for laser ablation. Okay, we can see your presentation.
Great. And can you hear me properly?
Yes.
Great. Please. Okay, then I would like to start. So first, hello everybody also from me. My name is Marcel Wolf, and I want to take you today into the world of the high-speed scanning systems, mainly focused on the polygon scanning systems. I bring with me today some process videos to show you how we can handle the high-power lasers together with the polygon scanner for fast, effective processing. So I have everybody has a good internet connection. But first, I want to introduce myself and give a short introduction of the Laser Institute of Mittweida. So I call it our laser expertise. The Laser Institute of Mittweida is located in Saxony and is one of the leading researching institutes of laser technologies in Germany. 50 employees are currently working in our institute, and we have more than 70 lasers with all kinds of pulse durations and wavelengths. So we are very flexible in terms of lasers which we can use for different applications. And we are well known for high throughput laser processes, like, for example, done with the polygon scanning technology, also for laser micro and macro machining and 3D printing technologies. To get a slightly start into my presentation today, I want to give you a short introduction. Yes, the laser is well known for the most of us, like the tool of the future. The industry demands tools like I summarized here on this slide, like directly, flexible, and so on. And all of these characteristics describes the laser quite good. So in our time, we have so much different materials in industrial applications, and it's all time only a question of the wavelengths and the pulse dimensions, the pulse durations, and you will find a laser finally which suits your demands of the process. Rough and also precise work tasks are realizable, and everything it's done with laser systems. So, but not only the lasers have needed for a good process, also optics have to match to your process as well. So I give you here a short overview about the basics of the beam guidance, so-called. So let us take a look of the kind of the optics which we have in industrial applications included. For example, static optics, moving optics, and the issue of today of my presentation, the scanning systems. So I summarized where are they used. Maybe we go further in terms of time. So I have to bother you a little bit with theoretics about the basics of the beam guidance, so how the scanner works. So I want to start with the galvanometer scanner. It is a two mirror scanning systems, and both of them mirrors made pendulum motions to realize a free-form beam passes. But due to the pendulum motions, we have accelerating and braking times in our workflow, and this limits finally also our achievable deflection speed. Another disadvantage on these systems is that the laser beam stays static on the first mirror, so also the power destinies are being limited. Deflection speeds up to 15 meters per second are achievable, and it's very effective in free shape processing. So now I want to speak about our polygon scanner. Where are the differences? It is also a two mirror system, but we not have two galvo mirrors. We have one rotating polygon mirror and one galvo mirror. In terms of this architecture, no free shape processing is possible. We realize our processing like an area, line by line. So the scan field finally consists of a slow axis and a fast axis. Due to the rotation of the polygon mirror wheel, the fast axis is generated. So each facet, by the rotation of the polygon, generates one high-speed line. After the polygon, the laser is deflected on the galvo mirror, which generates the so-called slow axis. When the facet is changing, the laser is switched off, and the galvo changes the position. And in this, like I explained now, a 2D scan area is formed. Due to the rotation of the polygon, we have no braking and accelerating times in our workflow. And yes, we using this to reach extremely high deflection speeds up to 1 kilometer per second. For a better understanding, I include here an animation that we understand how the scanner finally works. I hope it's for everybody proper. Yes, it works. So here's our 2-day scanning system. Maybe some technical points on this. On this point now, we have a 30 millimeter free aperture, which allows us to use all high power lasers on the market. The raw beam sizes to couple into the scanner are usually around this 14 millimeters 1 through E square. And here you can see how the 2D area is formed by the fast axis and by the slow axis. And now I include a slow motion, and you can see how each work line is generated, how the laser is switched on and switched off. And the distance between the lines is so-called hedge. We have to save this word because afterwards we need it. So that was the animation video. So now I want to speak about the features of the polygon scanner. So now we understand how the scanners work and where are the differences. So now I want to speak about the basic functions of our scan system. The polygon scanner has no fixed f-theta optic, so you can choose the optic which is the best for your application. Furthermore, the scanner comes with an optic ring with an bayonet lock, which makes the changing of the optics very fast, dependent to the chosen optics, the focal spot, and the maximum deflection speed and the maximum scan field is defined. You can change in the poly control software, which also came with the scanner, the scan field sizes. You can define objects. In your scan field, you can change the hedge, so the distance between the single working lines. Also, like define a subhedge. This is used to shift your working line through your scan field. You can set output signals and other external triggers. So a lot of stuff we will see later in the presentation. So we're very flexible in work. And I also include a video of our milestone, which we achieved. In this video, you can see an example of a full field operation. So with increasing scan speeds, the hedge, so the distance between the lines, all stays the same. And we only make the deflection of the laser beam faster and faster. Here we use a 420 millimeter f-theta optic, which has a maximum scan field of 300 to 300 square millimeters. And we tested scan speeds up to 500 meters per second. Afterwards, we tested also with this optic and achieved this 1 kilometer per second is possible with this optic and the full speed of the scanner. So, okay, now we can see the 500 meter per second, and then we stop here the test because we achieved the milestone. So, okay, but now enough about the basic functions and so on. Let us take a closer look to the high power laser processes. I made for you here an overview about the laser-based manufacturing processes in general, but due to the limited time today, I want only to speak about the cool ones, the separating materials, so like, for example, engraving, marking, drilling, and ablation and structuring. I bring with me, first we start with the drilling process. I bring with me a video of a drilling process. Here we can separate, this is now a one-pass drilling application of a very thin foil. So each pulse of our laser realized one hole. So, but here we got also a problem. Due to the thermal stresses of the thin foil, the foil can be teared. So, but also here, the scan system has a suitable solution. Due to the single line operation principle, we can jump not only one line distance, we can jump with the galvo every distance like you prefer. So that means we can form thermal fields and can distribute the energy over the area so that we can avoid the tearing effect. Yes, in this video we have to see seen that 125,000 drilled holes in this short time, and but not only we can drill through thin foils. When the substrates are thicker, we can use the so-called multi-pass drilling application. This opportunity our scanner has also, but here we are faced with other problems which I want to explain you. And we developed the so-called pulse-on-demand mode. Like you know, at higher speeds needs also higher precision. When the substrates get thicker and we need more than only one overscan, for example, like we will see soon in the drilling process video, due to the uncurrency of the laser pulses in the line, so a line is formed by more than one overscans, like you can see here in the pictures. For that problem, the scanner in combination with the right laser source has also the solution, the so-called pulse-on-demand mode. The rotation speed can synchronize with the output signals of the polygon scanner. And yes, then you have the ability to place the laser dots very accurate on each overscan, like shown in the right picture when we use the 10 overscans with the POD mode. And with this modus, you can change the position or hit all time the same position to form finally the hole. Also here I bring with me a process video. Here we can see a multipass drilling process of a 200 micrometer silicon wafer. The position of the polygon wheel is synchronized with the rep rate of the laser system. As we can see, the laser is guided really, really fast over the surface of around 200 meters per second. And yes, if the modus works, then we should drill through the substrate, and we will see it in the next slide when I show you the experimental results. So here is the summary of the experiments which I shown you in the video. Like we can see, the substrate is completely drilled through. The drilled hole looks not perfect circular, which comes from the long pulse duration combined with the high scan speed. Which stretched the laser pulses in the fast axis. Furthermore, we can see some material residues which also can be explained with the long pulse durations. The advantage is clear. It is a highly fast process and a very accurate process at the same time with the right laser system for sure. But before I show you the next application, I want to explain you short why the results looks like this. So again, again, a little bit theoretics behind the processes here. A drilling process we can separate in melt drilling processes and sublimation drilling processes. Here we can see in comparison a nanosecond laser pulse compared with a femtosecond laser pulse drilling application. I think the difference are clear visible. Just a short look into the theoretics to understand why. At the melt drilling process, the material gets molten, and in the middle of the melt pool, the material becomes to a steam and pushed out the molten material out of the drilled hole. So the resolidified material residues are on the drilling edge, and the process is very effective, no question, but has not so much quality. Now in comparison, the sublimation drilling process, here the laser pulse is so short and intensely that the material immediately becomes to a steam, so no molten material is involved. The material gets revolved in very thin layers. So I summarize it short: no melting zone, the material gets sublimated, and high quality edges. Okay, but slow. Here I bring with me some examples of drilling applications. For example, some kinds of filters in medical application or something like this. So like we can see, there are areas should be formed with drilled holes. And here are the scanners, the tools which are needed. You have two possible ways to drill it with the scanner, with the scanners, like you already seen the multipass drilling application, or you use galvo scanners, jump to this position where you want to make your hole, then turn the laser on, and then just wait till the hole is formed and then turn it off. Okay. So that's maybe enough to the drilling processes. Let us come to the next feature, the so-called BMP mode. What means this? BMP mode means the bitmap modus. With this mode, we can proceed grayscale pictures. The scanner has an internal memory of 1 GB where informations can be stored. And if we activate the BMP mode in the scanner software, the scanner modulates itself the signal that if you loaded a BMP picture, a grayscale picture into the scanner, activate the BMP mode, and then the scanner itself modulate the signal which you needed to proceed your logo, for example here this pulse logo, into your substrate. So we have the opportunity also to rescale the loaded data. For example, we can scale it much smaller, and like the scan field, and can fill up the scan field with the repetition of this loaded picture automatically, just with one push, and everything is done. For a better understanding from what I'm talking about, I also come with an process video where we realize that. We structure here this pulse logo, which you see on the slide before. So the first gray value which we engrave, what structure, is the pulse word. Like you can see now, I hope it starts, yes. Like the pulse word and the outline of the triangle. So the second gray value is the filling of the triangle. So like we can see in the next overscan, the internal scanner electronics will summarize this both gray values and then yes, structure both of them. So afterwards we can see the rescaling function. The process parameters are here summarized on the right side. So we use a laser with an average power of 500 watt and a pulse duration of 60 nanoseconds. The scanning speed was set to 250 meters per second, and the hedge distance was between 25 microns. And now you can see in the video how I change it on 2000 micrometers, just to show you how flexible the scanner can work and to achieve a better contrast in the final result. So now you can see the filling function of the scanner. It is all the time in this video, it's the same data set. I just rescale it, make it smaller, and push the filling function of the scanner, and the rest the scanner does. Just for your information here, the scan field size was 300 to 300 square millimeters. So we work again with the 420 f theta optics to use the full scan field size. So, and this is now the last overscan. Also, the scanning speed is the same, only the hedge distance was changed. So the operation time was here 1 minute and 20 seconds. So, okay, but we can do more with the bitmap modus. Before I show you the next cool application, I want to explain you how an engraving work task. Now we see a structuring work task, but now we want to transfer our informations into the material, so make some deeper surfaces. Okay, we can use this BMP modus for engraving work tasks as well, due to the 8-bit format. In an 8-bit format, we have 256 different gray values. And the scanner can proceed gray value by summation, like you see in the video with the triangle and the pulse, we shifting through the gray values by a Z shifter. Imaginable like by a 3D printer. So we're working slice by slice. Only we not apply material like a 3D printer, we laser it out. So we will removing it. So we start at the gray value 0 and incrementing till we reach this 255, and then all information should be transferred. Also, like I try to show you in the pictures here, also here we can scale the data set into the software and set the final structure depth by the number of crossings per gray value. So let me explain more in detail by example out of our pulse project. So we take our structure. This was the structure which we want to engrave. We save it as an STL file. We slice it into 256 slices and give each slice a gray value. And then we save it as an 8-bit BMP picture. Now we loaded this picture into our polygon scanner and irradiates slice per slice. The black areas means the laser is on, and the white areas means the laser is off, like I try to show you here in the picture. So after the irradiation, we increase the gray value of our data set and irradiate the next slice. So we start at 0 and ends up by 255, and the adjusting, we realize it by the structuring depth over the number of irradiations per gray value. So here I bring with me some examples which generated, for example, our institute building on a coin, yes, or for example, this what you can see in picture B, this spiral-like structure. So let me summarize it for you. This work mode, it is a scanning method for treating small areas and also large areas. The laser beam can guide it very accurate over the surface and transfer layer by layer the informations into the workpiece. Yes, and now I want to speak more about the process development, what we do into the pulse project to generate this, what you can see in small scale in the picture Z, this texture for in the pulse project, we want to create engraved mold. And after we convert the needed structure, like I told you, into this BMP file, which the scanner can proceed, we take a closer look first on the materials because we want to establish an effective process. So we find the best parameters to engrave this structure, like here in this slide described. Like you can see, the experiments shown that we achieve with 18 crossings per gray value, at 3 joule per square centimeter, a structure depth of around 19 microns. So here's the summary of the process parameters which we needed to achieve this needed 100 micrometers with an optimized process time of 90 minutes. In the picture, you can see a measurement of a structure which has a depth of 150 microns. So you can, I only want to show you can even deeper like you prefer. Just adapt the crossings per gray value and you can do whatever you want. After the single pattern was engraved and the process was optimized, the results should be transferred into the large scale that we can make a flat mold. So we have two things to do here. First, we have to evaluate the impact on the scan field size to the resulting structuring quality. And second, we have to stitch our data set together to enlarge area. Okay, this we have done. We achieved, here is seen the summary of the flat tool molds, which we engraved. The structuring of the whole plate needed 20 hours. So it means we have an engraving time of 20 square millimeters per minute of final surface. And to evaluate the quality of the structure, we measure it 9 times on different positions over the structured area. And you can see the measuring results here. So as we can see, all parameters are in the good range. The structuring depth is all over the plate in the right range. And afterwards, we send the final tools back to our partners for the further plastic injection tests. A little spoiler here, also this was successful, but we will listen some more information and more detailed information from the other speakers later. So everything is fine and everybody was happy. Okay, but now I want to speak now about another work task. We speak all the time about processes where the scan field is large enough or larger, like the workpiece what should be proceeded. But what we do when the workpiece is bigger, like the scan field. Also here we have already the solution. The scanner has external encoder interfaces for external systems, for example, linear axis or rotating axis. And internal, the scanner has shifting registers, which recognize movements and react on it in close to real time. So that means you are able to shift the data set which you loaded, or the whole scan field, or you shift the whole scanner system, or the plate, the workpiece under the scan field, everything what you want in all directions. And the scanner will react on that. So like I tried to show you in this animation. And all this work about we speak now, we can also combine. So I bring with me a process video which is really fancy and combined the most of the features of the polygon scanner. Here we can see a structuring process of a Jaguar with an ultra-short laser pulse, with an ultra-short laser. First, the slow axis is realized by the galvo, but also we can, like I told already, combine this with an external axis system. So now we can see the X synchronization mode. So like you can see, the scanner is reacting in close to real time on the moving of the surface and yes, adapted like you need your output signals. With this mode, you are able to manufacture substrates which are larger like your scan field by shifting the whole scan field or like you prefer. Again, I think you see it already. You're really flexible how you want to realize your work tasks. And with the polygon scanner, it's all time away. And here you can see how the slow axis is combined, realized with the galvo and together with the axis synchronization mode. So everything is possible. And this is the nice view with the ripples when you used femtoseconds lasers together with polygon scanners. So okay, yes, I want to. I hope I can give you an interesting overview about the processes where scanners in combinations with high power lasers are used. And I also hope I was able to show you what is realizable with our scanning system, and that the application fields of the polygon scanner are expanding every day. I mean, the continuous development of the laser sources needs also and further development of the scanning devices. So I think we have seen in this presentation what we are able to do with the scanners, and that the polygon can give us more performance if the right laser is in place. So let me close my presentation with the final statement. Like I told before, the lasers are the tools of the futures. It was not correct. The lasers and the scanners are the tool of the futures. Thank you, and I'm happy to answer to any questions.
Okay, thank you, Marcel. Do we have questions? Yes, Marvin, please.
One question: what is the transmission through your scanner?
You mean the percent of losses which
Yes.
which we achieved? Yes, we use anti-reflective surfaces also on the optics and the mirrors and transmission windows and so on. So you have losses of maybe around. It's all time a question of what laser you use. We also have, for example, UV scanning systems. There are the losses quite more, around this 20%. But with this near infrared, we laser around of maybe 10% maximum.
Okay. And if I have seen it correctly, your polygon is gold coated.
Yes.
Is it correct?
Yes.
What is the problem with the damage threshold in this?
Yes, we also investigated this into in our in the Pulse project. And there we see that the weakest point of our scanning system is not the polygon mirror, our goal, that is by 0.6 joule per square centimeter. The weakest point in the scanning system is the galvo. And the galvo lays by 0.2 joule per square centimeter, so also quite large. So we have a safety factor from the developed pulsed laser to the final destroying our scan system of 1000. So we're not even in a danger zone, I would like to tell.
It's a bit surprising because I thought the galvo mirror is a dielectric mirror. So
yes,
this should be higher in LIDT in comparison to a gold, which is for sub-picosecond, it's in the 0.1 joule per square centimeter, not in the 0.6. So maybe the 0.6 is for nanosecond, was it? Or for...
No, we used femtoseconds to evaluate that.
Okay.
Yes, we also was surprised about that. But we think that the problem is by the dielectric mirror is inside, because you not have so much material to get the energy out of the surface. So maybe that is the reason why it's damaged so fast.
Yeah, but this is only for nanosecond, not for femtosecond. The damage threshold process is completely different.
Yes,
you don't have this heat dissipation, aspect.
Yes,
okay,
but
but
also...
it's very, very surprising, and especially for femtosecond and gold coated material having 0.6 joule per square centimeter is surprising me actually. But
yes, we was also surprised about that values. We also think that the first which get destroyed is the polygon mirror.
Yeah, very impressive. Congratulations. Yeah, thank you.
Thank you.
Okay, other questions? If not, let's move forward. We're a little bit behind the schedule, so we have 3 more talks, and the next speaker is Oliver Steffens from Lunovu, and he will talk us about the fantastic and versatile laser processing machine.
Yeah, thanks, Regina. I'm going to share my presentation. This one. And,
yes, we can.
Is this the right format now? Yes. So.
Yes, we can see it and we can hear you well.
Okay, great. Before I start to talk about our task or our objective in our PULS project, I just want to lose some words about our company. So our company is called Lunovu, and this is founded in August 2013. So it's a quite young company. And we see us as a spin-off of the Fraunhofer Institute for Laser Technik in Aachen. We are about 25 employees right now, and we are building so-called intelligent laser machine systems, and we are focusing on microprocessing and at least also on laser metal depositioning. In this, and we are specialized in additive manufacturing or cladding. We do have an in-house process development. In between, we have 3 machines in our application center, and perhaps what is special about our staff is that we have a huge IT and software background, because we are thinking the processes in microprocessing and also in additive manufacturing must be or can't be handled without some kind of software and some kind of intelligence within the systems and within the machines. So this is a view to our products or to our machines we have built and sold. On the right-hand side, you see this. The most of the things we sold are in the macro processing field. So this is mostly laser metal depositioning or coating. And on the left-hand side, you see some of the microprocessing systems. And what is very special about the microprocessing systems is that they are all built, or often all built, for only one special application. So it's always a special machine what we are designing. And in macro processing, we use same kinematics, same machine components. So it's a little bit different from the approach when we're designing a new machine. But later on, I will tell you what's the special thing about this in our PULS project. A few words about me before. So I am one of the managing director of Lunovu. I've started my career by studying computer science in Passau, somewhere in Bavaria, in deep of Bavaria somewhere, and finished it in Aachen. There I started to work at the Fraunhofer Institute, and this was, to be honest, I was thrilled by laser technology right from the start. And so this is a thing where I left my heart, and then it's always a thing what I'm doing today. We started my first company in 2001, dealing with software and controls only, and started Lunovu in 2013, for me in 2014, but dealing with machine building and building complete systems or laser treatment at least. So I'm responsible for development in our company and also for the finances. And so this is the reason why I am with you today. Within the PULS project, we are somewhere between all the developments we have done in the, or base developments we have done in laser technology, and the thing what Marcel told us before. So we want to scale up all the system for industrial usage. And so what we want to do is we want to build a machine where we can use all these things what we heard about today. So there are two buzzwords within all this text. One is the laser machining system, what we have to design and to set up. And the other one, what is quite important, is the complete control, including all the software development, what we needed. We started by a look to the requirements we need for the applications we have defined in the proposal. And also here you see the combination of the macro processing and microprocessing, because on the one hand, we want to treat something like a boron steel in B pillars from cars, or want to weld copper and aluminium. And on the other hand, as Marcel showed before, we want to microtexture injection molds. So at least we have some certain requirements or some new requirements on the machine design. So on the one hand, we have we need some great dimensions to handle all the workpieces we have defined. So we defined somewhere around 1 cubic meter. We need some kind of 5-axis capability, because we have to process workpieces with different orientations and in different positions. For example, when we want to cut a hole into the B pillar. But on the other hand, we need much more dynamics and accuracy. When we compare that to our standard macro processes. So we need a big machine, but it must be dynamic and it must be very precise. And of course, it has to combine all the things we have developed within the project. First of all, the polygon scanner, of course, and the laser at least. And but we also must take into account that there are some other things what we need when we are processing. So we have to look for the gases, for the cooling, for exhausting, and also, of course, and last but not least, for safety. So we are also thinking about new housing, because the laser system is quite new, and we have to check that our safety systems are compatible with all the things what we have developed within this project, because the laser source is very, very strong. So on the other hand, we need some control and software development. So what we have to do is, Marcel told us before, you are able to combine the polygon scanner with the laser or with the machine control in that way that it works together. So our task is to use something what is well known. As for example, the control we use is one from Siemens. This is the one what we always use in big machines and macro processing machines. But this also must have the interfaces and all capabilities to integrate the laser and also the polygon scanner. And then we need some electric technical and some software development to put this all together. Always thinking about that we have 3 modes of operation. We use it like a CV laser when we are going to weld or when we are going to cut. We using it as Marcel has shown before with the capability of pulse on demands. And there's another thing what we have been talking about within this project. There's also the pulse burst what we can use. And so we set up a new design or architecture of our complete control environment, starting with the Siemens control at least. And okay, this is something that is not working. Okay. And we have the polygon scanner controller, what we have to integrate or implement, and also the laser controller that must work with the polygon scanner and also the control. And of course, some is something like an industrial PC, because we need something to show all the user interfaces, and we want to have possibility to monitor all the processes we want to perform. All these things are connected on the one hand by Ethernet. This is just the actual standard interface to connect things when we have more than one intelligent system within our control system. Then there are some standard general IOs, digital IOs, analog IOs, which are very slow when these are thought for getting things into operation, just to say the laser controller, okay, start a laser, or be ready to that you will okay, get the laser in ready for operation mode, something like that. Or if you want to start the polygon scanner at all, just to rotate. These are quite slow signals, what we can control via the PLC of our control. So there are things, there are commands within our numerical control program to start and stop and supervise all the things. And there are some fast or very fast interfaces, for example, what we need for pulse on demand, so that we connect the polygon scanner controller directly to the laser I/O to have the full control of the laser via the polygon scanner. And then we have to combine the information of movement of the big robot with the polygon scanner, and that we are doing with the encoder signals, which are also connected to the polygon scanner controller. Okay, this for the start of the design of the complete system. Then we started, of course, the mechanical design and setup, and we started with something what we know from our macro systems, because we have a big workplace, we have a big working area. Then we analyze what we have to do better than our machines, what we use for L&D or something in the macro processing. And the first one, of course, what we see is that we must get more precise. And more precise is not only a question of positioning of the robot or moving the robot, it's also, and this is much more complicated, a question of vibration. For example, when we accelerate or deaccelerate axis with some mass at the Z axis, there's something happening in the machine. What perhaps you can even see, but in microprocessing it can get very important. So what we have done at first is that we have done a lot of analysis of our machine base, and we have done some vibration analysis, as you see above, and have made some optimizations of our connections between of all our axes, and also of some materials of our complete base. And after that, we were quite sure that we are able to handle all the workpiece or all the tasks we have seen in our proposal. And then we started to build the machine, at least. What we also did, or what we also knew, is, of course, the control itself is also capable of optimize some things of the machine. For example, you can measure the complete machine's positioning accuracy and integrate some compensations into the control for make it more precise and more dynamic than before. Okay, what you see here is some pictures from the control setup and software engineering. So we have done this parallel because we didn't have so much time to realize all these things. So we started with a testing environment, as you see left above, that we had all the controls things and electrotechnical things we have developed in the same time as we set up the complete machine. And we also integrate the polygon scanner very early into the machine, just to check if all the things that we have developed is working. And yes, of course, we had to do some optimizations after that. So everything was quite fast at the beginning of the project. And on the right-hand side of the slide, you see the complete machine set up before our demonstrations. Okay, if you have a look into the machine, you see some details. Okay, we left the ceiling open because we did not know how to guide the fiber. You see some housing or tubing at the Z-axis where we guide gas, air, and all of the cooling. And of course, you need some exhaustion or extraction. This is also done. So we are, it's completely, all media we need are supported now, and we are completely ready for operation. On the right-hand side, you see the holder for the polygon scanner with two alternatives, how to connect the collimator and the last mirror to the polygon scanner. And so we started, the integration of it. This is a video. This was quite early in the project, as I told you, where we tested the polygon scanner and its capability to use it with robot positioning axes simultaneously, and this worked very well. And you see in this case that this is moving from right to left, but it is also possible to move it diagonal, and what you can see here. Yeah, and also we are able to turning the complete workpiece, and then moving to somewhere where it is not processed before. And then you will see that also this is possible, and this is all these things are done with one setup. So I have to agree with Marcel. His polygon scanner is working very well, and we are able to structure a very large field or a very large area within our machine. Okay, then of course we did some preparation for the workpieces we have seen in the proposal. These are the things what we wanted to process. Beginning on the left-hand side with a B pillar, where we need a lot of the workpiece area, and we need all the access to process. The reason is we want to cut holes or perhaps just make a cut into the bronze steel. But we need the complete machine functionality for that. A little bit more easy is to cut the aluminum foils. Therefore, we have some holder. This is another thing that the flatness is very important when we use the laser with these aluminum foils. Then we had a mold. This is a quite heavy workpiece, so there are some requirements towards a turning tilting device. But also this is working. Okay, Marcel showed the principle of it. We had to structure it level by level, but we are able to orientate that workpiece towards the polygon scanner as we need that. And the last thing is what we wanted to do is we want to weld or join the similar materials like copper and aluminum within the machine. So at least this machine is prepared for all the demonstrations or for all the applications what we have defined at the beginning of the project. Okay, we demonstrate this functionality at least with another kind of laser, and we use for that the Trumpf laser. This is a nano 1010 laser. It's to say that this does not have at least the power of the things what we were talking about in pulse, but this demonstration just should show that our controller machine is working. And so these are the characteristics of the laser. So what you see is that it's about average power for 100 watt, and this is a nanosecond laser. So it's quite weak when we compare that to the other things what we see from Marcel before. The setup here is that we put the Trumpf nano laser directly to the Z-axis. There are some electronics above it. They are not very interesting, but these are the connection to the controller of the polygon scanner. What you see is the fiber, which is connected to the laser, as well as to some optics before the polygon scanner for the adjustment. The polygon scanner itself, below the f-theta lens, and yeah, there's no workpiece now in the working area. In front of it, you see two screens, where we on the left-hand side is our standard user interface, our standard machines. We also have the Siemens HMI on it. On the right-hand side, you see we have put that in addition to the left one, because we also wanted to see, of course, the interfaces of the polygon scanner and of the laser. So with this system, this is just a flight to the setup from bottom to top. And our first demonstration was just to cut something in aluminum foils. This is a setup, and what is happening then is what you see here, where we move the polygon scanner above the surface of the aluminum foil, and you see some kind of structuring in the foils. Okay, we have a problem, of course, with this holder of the flatness of the foil. But what we can demonstrate is just with this weak laser, we can cut something into the foil. And this is not, the laser is weak because the laser is weak, but I think you can imagine if you have a high power laser, then it's, of course, structuring is possible, and also welding, cutting of this foils is possible with high speed and with these modules in our system. So what we tried here is quite interesting, because what you see on the left-hand side is thermal paper, what you know from the cash desk in the supermarket, and we try to generate our logo within this paper. But when we started to work, then the polygon scanner is so fast that it distributes the power so fast that the thermal paper does not even get warm. So what to say? Perhaps it's a good result, because all things is working. The bad thing is you don't see the logo. Yeah, on the right-hand side, so you see, this is running. Yeah, okay, this was running. On the right-hand side, you see the interfaces. This is just to see that the polygon scanner is ready. These are the PLC signals, the slow signals. This is the interface from the laser, where you see this is in similar state or in active state when it turns on and turns off the power. And on the right-hand side, you see the well-known interface from Marcel from the polygon scanner, where we are in bitmap mode for the attention to generate the pulse logo. Okay, then we try to join glass and aluminium, but okay, this we knew this couldn't work because the laser is much too weak. But what we could achieve is we could make a scratch on the aluminium plate through the glass. So this is a very good material, because there are nothing reflects the laser within the glass. Sorry. What reflects the laser in the glass, but the glass itself wasn't affected at all. So the last thing, okay, this was just to show the 5-axis capability of the machine for the boron steel or for the B pillar. And so what you see here is that we are able to orientate and to move the polygon scanner in the complete working area, also to process big work pieces. And so we also need this capability when we are going to process the B pillar, at least. Okay. Okay, this is a treatment of the B pillar. And as you see on the right-hand side, we made some trials on the surface, on the flat surface before, and then we started to treat the side. And for treating the side, we need all the functionality of all components, moving the robot and moving the workpiece with 5 axes. Yeah, okay, this is just a summary of what we have done. What you see is the structured surface, the laser beam, 5 axis, and what I told you, the combination of the movement of the axis and the usage of the polygon scanner. So at least we have developed and set up a laser processing machine for industrial usage, which is capable to micro and macro processing, a combination of it. What we measured is a positioning accuracy of the complete system and the complete working area better than 0.1 millimeters. I think it's something about 50 or 30 micrometers. Pass accuracy about 0.1 millimeters. And yes, of course, it's 5-axis movements is possible within a combination of control scanner and laser. User interface is accessible and is working, and our process demonstrations are done. So with this machine, we have scaled up at least our lab environment to an industrial system, and we are ready for integration of a high power pulse laser and waiting eagerly for it. On the other hand, a side effect, of course, is that we also improved our machine base for the other applications we are talking about. Yes, the macro processing like LMD and cladding. Yeah, and I think that we have done, all in all, we have done a good work within this project, because we have, with this system, with the high power laser, we get access to a new range of applications. So this is what I wanted to tell you, and I thank you for your attention.
Okay, thank you very much, Oliver. And we're open for the questions.
I have a quick one, sorry.
Sure,
typically for microprocessing, the people are asking more and more about precisions in the micrometer.
Yeah.
Not in the 100 micrometer. What will be the next step for you then to go in this direction?
Yeah. Okay. Also, first of all, this accuracy is measured in the whole working area. If we are talking about a smaller area within the middle of the machine, we are much more precise. And yes, you are right. If we are going to make applications by stitching fields together with the polygon scanner, then we will have a problem with it 0.1 millimeters. But when we are going to move the axis and using it simultaneously, we hope that we get that we achieve better results, especially if the fields are not as big as I showed in the first demonstration when we are using the complete working area. But we have to measure that. You are right.
Okay, thank you. But very impressive anyway. Yeah, thanks.
Okay, other questions? If not, let's move. So we have two more short presentations from the application area, and the first one is a laser welding given by Elias from Laser Prime Technology. Yes, now we can see it in the presentation mode, please.
Okay, thank you. My name is Elias Hontzopoulos, and I'm from the partner of the project Prime Laser Technology. I will show you some information. This is the context of my presentation. I'll give you some information about our company, the market and production, and then I will move to the laser welding that we are interested on. About our company was founded in 2006. It is a B2B manufacturing in solar thermal absorbers. Currently, we are about 24 employees, and we are located in Keraten, Greece, close to the Athens airport. The solar thermal application is used either in buildings and houses, but also in the industry for heating processes or for cooling, but also for the teleheating application, either directly or in combination with other source like biomass in this picture in the center. This is the market in Europe. You can see that the biggest market is Germany, and the second one is Greece. And talking for Greece, you can see here how the production is developed in the last years, and about 70% of the local market, local production, it is exported. Talking about the production in Prime, we are producing mainly the internal part of the solar collectors, which is the solar thermal absorbers. And this is combined by copper tubes and selective surface that absorb the sun and transfer the temperature. These are some of the product, and the installation in different areas is not only for the thermosiphon system, but you can see different application in Dubai and to areas, but also in Chile. It is when it was performed, this was the biggest land laser solar field in the world for heating, provide heating to Codelco mining company in Chile. In our case, we, as it is already mentioned in the past, we weld dissimilar materials, aluminum and copper. We are building, we are making spot welding. As you can see, these two photographs in reality and in a sketch. And actually, we are using in our production line anti-yak lasers with 0.3 to 0.4 millisecond pulses. And we are mainly, actually, our welding sport is ablation welding, the process we can describe, because we ablate material from the surface to build the welding spots. And these are some information about the materials that we're using, and these are two systems that we have in operation. One is pulse and the yak laser, and another one with a fiber laser, and with different possibility. The second one, we are using a 6-axis robotic arm. Actually, what we are doing, we are welding from both sides of the tube. So we have two beams are coming directly to the area that is in the area below, between the tube and the surface. You can see the process here that we ablate material from the aluminum surface, and we move towards the copper tube, and this way we produce the spot. Here you can see that the spot, inside the spot, we have different areas that are bimetallic materials and different phases with different properties, and this is very important to control the process parameters in order to have the correct welding. Here you can see some welds that we have performed with our fiber laser, and this was some tests that we performed during our Pulse project with the robotic arm and modulate fiber beam at up to 120 meters per minute. And of course, we proceed and we characterize this kind of welds and have some information. And here are some information, some picture from welding with nanosecond pulses, copper, aluminum to glass. And these are some trials that we have performed in Mittweida with nanosecond pulses in these cases. And you can see that there is areas that the glass was welded to the surface. And of course, we need to optimize this application. This was my first presentation. I'm ready to give you some information, some answer if you have some questions. Yes, Marwan?
Yes, a quick question. And you have shown very nice result with the CW or millisecond lasers.
Yes.
The project is aiming picosecond, femtosecond. What will be the benefit from your perspective using second laser?
The problem that the problem is not exactly a problem because the market is accepted. But if we go back a little bit, you see that there are some surface structure due to the forces that are kept inside the material. Mm-hmm. So we like, you see in the center that we have some buggles. Yeah, we like to take out this because this is a thermal effect on the surface, and we like to remove this. And from the other side, what we like to do is to move as fast as possible without damaging the surface, because the other side of the surface coated by temperature. So we like to have as cold as possible the welding process.
Okay.
If we can use this expression.
Yes, no, makes sense because I mean, ultra-short pulses are meant for this.
Exactly. And for the glass to metal, what is interesting for us is not just to weld, but to keep vacuum in order to make application in our field.
All right. Okay, thank you.
You're welcome.
To the last but not least presentation in our program, and it will be about laser engraving for automotive injection molds, and it will be presented by Gianluca from Stellantis.
Hello, everyone. Hoping can you hear me, see me, and also see my desktop as well?
No, yes, now it's yes.
Okay, so also in our case, a fast presentation about more or less 10 minutes about the results we achieved with the high-power ultrafast laser for engraving used in the injection molding process in automotive industries. So the presentation is divided in few parts. A couple of slides just to talk about our new organization, Stellantis. Then I will show you some results that we achieved for the injection molding process. So why we want to use a laser for the injection molding and some results and assessment that we achieved about the morphology that we use as a reference morphology. So I will describe what the reference morphology is. Then I will show you some results on the metal mold and the final plastic samples that we obtain, and then also some results about the 3D samples that we obtain also with the injection molding process. So, as I said, some words about the new organization. Stellantis is formed by two, let me say, old organization, PSA, that is the French group, and FCA, the Fiat Chrysler Automobiles. Here are some companies that are making up the new brand. In my case, I'm Gianluca Deninno. As I said, I'm working under Nello Lipira, that is the manager, the global manager of material for electrification, but there are another groups for polymers and metals that are developing new technologies from a material point of view. Our activities are here just a slide to show some example of the activities that in which we are involved, internal and external activities, European project, and so on. So what about the injection molding? The injection molding is a industry process that is widely used also in the automotive industries. In this case, the laser engraving can be very useful in this process because the main advantage that we can obtain is the customization, as I will show you in the next slides. But then we can also obtain another benefits like the repeatability and the spatial resolution with the process. In this way, we can obtain very useful results in order to be applied for the optical surface, aesthetic, and the durability of the final components. Currently, the injection molding process is used, as I said, in automotive industries for the realization of internal and external components. Here, just a list of a few of them. So it can be used for trims, panels, but also for bumpers and fenders for the exterior components. So in this case, the injection molding process is divided in a few steps. The first one, as I said, the best benefit that we can obtain is the customization. So we can choose a priori the morphology that we want to print into the metal mold. We can measure this morphology through different instruments, in this case with an optical instrument. Then with this data, we can manage this data as has been showed. We can manage this data in order to give, in order to print this morphology into the metal molds with the laser, and then melting and injecting the melted plastic into the metal mold at high pressure and temperature we can obtain, as I show you the final plastic component with the desired morphology that we want to obtain. So what about the reference morphology? As I try to describe, the reference morphology is the morphology that we want to print into the metal mold. In this case, we measure a morphology that is already used in automotive surface for interior applications. So in this case, the characterization of the reference morphology is divided in few steps. We measure, as I said, in this case with a profilometer, that is a contact instrument, the morphology. We import this data into a specific software, and in this case, we have characterized from a morphological point of view in order to study and characterize the process and the quality of the process itself. So what about the assessment of the metal mold? As has been already shown, once the metal mold has been engraved, we measure in the same way the morphology that we obtain into the metal mold. So in this case, different metal molds have been studied, different morphological parameters have been studied. In this case, two of them that are considered from us one of the most important, the SQ and the SDQ parameter. And so we measure these parameters and we compare this parameter with the original ones. So in this case, in orange, the morphological parameters that we measure with the confocal microscope on the metal molds compare with the original value that are the values measured on the reference morphology. So in this case, we studied the morphology obtained into the metal mold as a function of the metal molds that have been used. Same characterization for the final plastic component that we achieve. So same morphological parameter have been studied along the surface of the final plastic component. Also in this case have been compared with the original values that have been chosen at the starting point of the activities. And then we characterized and we studied the difference between the morphology that we print into the metal mold with the polygon scanner and the difference between the differences observed in the PCABS samples. So in this case, with a particular software, first of all, we measure the morphology of these two surfaces. With a particular software, we can get those data and we can overlap these two surfaces. From an ideal point of view, if there are any differences on these two surfaces, if we can calculate the difference between them, if these two surfaces are identical, the difference should be zero. Otherwise, if there are some differences between them, the difference could be greater than zero. So in this case, we can see the differences between these two morphology. We can see that with a metal mold, the 2738 has been achieved. There is a mismatch between the final plastic samples that has been obtained with the morphology of the metal mold. For the final part of this presentation, I will show you some results that we achieved for the realization of 3D samples. In this case, we realized the fascia trim of the Fiat 500. And so we start with the CAD file of this object. Here some step used for the realization of the component. So it started with the modeling of the component, then the injection molding. So also in this case, the same process with PCABS samples and ABS samples, high temperature and pressure, and then also in this case the final evaluation that have been achieved with a morphological assessment of the final component with different morphological parameters, and also for the different materials that has been used, as I said, for ABS and PCABS samples. So the conclusion for this presentation, as Marcel said in his presentation, we are proud and happy of the results that we have achieved. We saw that there are a few differences from a morphological point of view if different metal molds are used. We verify some technical problems on transferring the morphology, the reference morphology of the metal molds, about the repetition of this reference morphology. But as I said, we are proud about the quality that we achieved for the 2D samples, but also for the 3D samples as well. And if there are any questions, doubts, I will be happy to answer to you.
Okay, thank you, Gianluca. Any questions? Okay, it looks like everything was very convincing. Thank you very much. And this is the final presentation. And on behalf of the whole consortium, I would like to thank all attendants for your patience and strong interest to your project. It was a very long day and hope you enjoy it. I'd like to wish you a nice weekend, and we can close this meeting now.